So we're discussing now AIM 9.2, special right triangles, coterminal, and reference angles. So what angle relationship do you notice with the triangles? Well, you may have noticed that the side that is opposite 30 degrees, in this case being 1, was half that of the side that's opposite 90 degrees, being 2. You can also see the same here, where the side is 3 and it's opposite 30 degrees, and the side that is opposite the hypotenuse is 6, doubled that of the 30 degrees. And every side that is opposite the 60 was the side of 30 multiplied by the square root of 3. And with the 45, 45, 90 triangles, you would have noticed that these are isosceles triangles and thus their legs are equivalent. So now let's derive those special right triangles. Where did they come from? So in trigonometry, there are two special right triangles. So we're going to first look at one of these triangles, the 30, 60, 90 triangle. Where does it come from and why is it special? So first, let's start off with an equilateral triangle. So for an equilateral triangle, it's of note that all sides would have the same measure. In this case, I decided to make each side worth 2. But an equilateral triangle has it fixed that all of the angles are also equiangular. So let's look at that. So this is 60 degrees, and this is 60 degrees, and this one is also 60 degrees. At this point, we're going to bisect this triangle. And when we bisect the triangle, for an equilateral triangle, the altitude is also the same as its perpendicular bisector. So it's going to cut these into two congruent parts that form a 90-degree angle. So I'm going to take one of those halves and we're going to examine it here. So now, if you'll notice, the hypotenuse is 2. And since we cut it in half, this portion here is going to be 1. The side is still 60 degrees. But since this is 90 and this is 60, this portion here must be 30 degrees because all triangles have 180 degrees. So how do we figure out what that missing side will be? Well, if you remember from the Pythagorean theorem, a squared plus b squared is equal to c squared as it applies to right triangles. So we can say that, actually let me put it over on the other side here. We can state that 1 squared plus b squared is equal to 2 squared. Now this is the same as 1 plus b squared is equal to 4, and b is equal then to 3. Oh, excuse me, b squared is equal to 3. Now in order to solve for b, we have to take the square root. Now oftentimes when you take the square root, you assume the positive and the negative. However, since we're talking about distance or a side length, we're only going to assume the positive. So b then is equal to the square root of 3. So it follows that this is equal to the square root of 3. And if you'll notice something pretty interesting with the side lengths, notice how the side that's opposite 30 is 1, and the side that's opposite 90 is 2. So the side that's opposite 30 is 1/2 of the hypotenuse. So the side relationship, side that's opposite 30, if this is x, then this portion here would be 2x. And I really could also just add a times 1, and that's not changing anything. And I could also put a times 1 here, and that wouldn't change anything either. So if the side that's opposite 30 is 1, the ratio is for 60 is x times the square root of 3. Okay, so now let's look at how we derive the 45, 45, 90 triangle. Okay, so next we're going to look at the 45, 45, 90 triangle. And how do we get the ratios for this triangle? So first let's look at a square. And a square has 90-degree angles, and all of the sides are equilateral. So if this portion is 1, then this is 1, and that's 1. I'm just using 1 as an example. You can pick any number. So now what I'm going to do is I'm going to bisect this square. And when I do that, I get the one that's below. Now notice how these two sides are still the same length. So if this is 1, then this will also still be 1. Now, how do we determine what the hypotenuse is? Oh, actually, before we even get to that, the nice thing about squares is that their diagonals bisect the angle. So if this is 90 degrees, half of that is 45, 45. So now we've got ourselves a 45, 45, 90 triangle. So if your two legs are 1, how can we determine what our hypotenuse is? Well, again, because this is a right triangle, we can say that 1 squared plus 1 squared is equal to c squared. So 2 is equal to c squared. And again, normally when we incorporate a square root, you would assume the positive and the negative. However, because we're dealing with a distance or a side length, we're going to assume just the positive. So this is the square root of 2 is equal to c. So this side length here is the square root of 2. Now, if you'll look at this, you can also think of this as putting a 1 in front of it, the one that would match up with the other two side lengths. So if we wanted to come up with a ratio relationship or a side relationship, you can think of the following. X, and x times the square root of 2. Okay, so now let's move on. So in trigonometry, next we're special right triangle. So the ratio for the 30, 60, 90 triangle is as follows. If 30 degrees is A, 60 degrees is A times the square root of 3, and 90 is 2A. For the 45, 45, 90 special right triangle, if both sides are A, then the hypotenuse is A times the square root of 2. Now, an angle is a measurement. The angle is measured by rotation of counterclockwise, and the terminal side is the ending side. So here's a demonstration of that. So in rotating circles in trigonometry, it's very interesting. So we have here what's known as the initial side. Notice how the initial side, it does not move. This will always stay as the initial side. However, the other portion of our angle is called the terminal side, and the terminal side is the one that moves. Notice how the terminal side rotates in a counterclockwise manner. When it rotates in a counterclockwise manner, that is known as a positive angle. However, if it rotates in a clockwise manner, like so, your angle is now considered negative. The rotation of the angles corresponds to the rotation of the quadrants. Quadrant 1, quadrant 2, quadrant 3, and quadrant 4. Coterminal angles are angles that meet at the same place on the unit circle. So that's a rotation of 180 degrees. And the other way would be a rotation of negative 180 degrees. Of note, negative angles are angles that are rotated clockwise. So just as if you were to rotate 30 degrees, you would have to rotate negative 270. Oh, no, that's a typo. Sorry, you would have to rotate negative 330 in order to reach the opposite side. That will be corrected on the slide. If you were to rotate 50 degrees, you would have to rotate negative 310, and 220 degrees, you would have to rotate negative 140. I like to think of this as the trig version of Sleepless in Seattle, and the point where they meet is the Empire State Building. So reference angles. For any given angle, its reference angle is an acute version of that angle. In standard form, the reference angle is the smallest angle between the terminal side and of the angle theta, and is the same with the trig values for the reference angle of theta. We'll get into the trig later. And this could be plus or minus a sign. So if you'll notice here, although your angle is obtuse, the reference angle is always acute. It's the distance that your angle is from the x-axis. Also over here, we're just looking at the acute form, and over here, we're looking at the acute form. It's always the distance from the x-axis, not the distance from the y-axis. And your homework is delta math.